From the previous video, we saw some examples on evaluating gamma functions like um, gamma 1, gamma 4, gamma 5, and gamma 3. So in this video now, in some cases, you might have fractional functions like gamma 1 over 2, gamma 7 over 2, gamma 5 over 2, gamma 3 over 2, just like that. So there are some exceptional cases that needs us to state or categorically state some proof or prove out some standard gamma functions like that before we can apply them to solving or evaluating gamma functions that are fractional. Okay, so one of the standard one that you can come across in your exam or test is proving gamma 1 over 2 and then stating it to be equal to root of pi. Yes, this you can always come across this in your test or your exam. So now I'm going to be taking us through how you can go about this right now. All right, so now we start from the general the gamma function of 1 over 2 now to be equal to the square root of pi. So this is the proof. All right, so this proof, you can expect that in your test or exam is always very constant. It's always a constant question they ask in either a test or exam. So please let's bear that in mind. We have dealt with gamma functions, beta functions from a previous video, and then I've always explained that these two are a twin. So now there is a connectivity between them, which is a relationship. Now in this tutorial now we're going to be treating relationship between gamma function and beta function. So it's always expedient for you to know how to derive this relationship because it can come out in your test or exam. So just know how to derive it, and then that's exactly what I'm going to be teaching you guys in this video, and how you can solve examples with this particular relationship and at least scale through your exam. Right, so from the slide you can see it's a beta function can be related in terms of gamma function as beta m comma n now is equal to, you have gamma m, gamma n is equal to gamma m plus n. All right, first thing is, okay, you see that the numerator here is what they are multiplying two gamma functions together. So that means you can have a gamma function that we have come to this end of the proof. Now I've said it's very expedient for you to know how to prove this in case of exam or test. So here I have some questions for us, which are very important questions for exam and test. So we have on beta and gamma functions. So we have the first one, you asked to evaluate integral of 0 to 3 x cubed over root 3 minus x dx, and the other one you have integral of 0 to 2. You asked to prove that, let's note this question 2 is very important, and from the square root, the cube root of 3 of 8 minus s cubed dx is equal to 16 pi over 9 root 3. So I'm going to start with the first one. And starting with the first one now, we have to evaluate this, right? That means since this is 0 to 3 is a constant, right? We are using a beta function, then you evaluate the beta function. And we know the general beta function is Okay, and this is the solution for what we are asked to prove. We're asked to prove that this integral now is equal to 16 pi over 9 root 3, and you can see it that we've proved it that is equal to 16 pi over 9 root 3. From the previous video, we did some um, useful integral functions now, which are integral and constants now, like use some conditions to know their values. Now in this video now we are going to be treating Fourier coefficients. If you want to find the Fourier series of a particular function now, I told you from the first video that this is the general formula of a Fourier series of a particular function, where a naught, ak, and bk are the Fourier coefficients. So they are the unknown parameters now in this particular formula. So that means we need to know how to solve for them. Solving for this Fourier coefficient now will enable us to be able to generate the Fourier series of a particular function. So now what are the expressions for this Fourier coefficient? So from the very first general formula of Fourier expansion, all right, so these are the three major Fourier coefficients that we need to find if you want to find the Fourier series expansion of a particular function f of x. In our previous video, we've treated even and odd functions and how you can know them, because we said odd functions, literally from the general Fourier series expansion formula, you only need to find bk, so a naught and ak are 0. Now for an even function, a naught and ak has value, or have value rather, whereas bk is 0. So now we have an example to solve here. Example 1 says find the Fourier series of the non-periodic function f of x equal to x squared in the interval of minus pi less than or equal to x less than or equal to pi. All right, so since we already ascertained that x squared is an even function, so that means from our f of x, now we have the final expression for the Fourier series expansion of x squared now as an odd, or sorry, as an even function. Example 2, where we have find the Fourier series of the function f of x equal to minus cos x for negative x less than or equal to x less than 0, and is equal to cos x for 0 less than x less than or equal to pi. So that means your the interval now for integrating cos x here now is going to be 0 to pi. The interval for integrating negative cos x is going to be negative pi to 0. Yeah. Now we need to know whether this function is an odd function or an even function. So you can start by finding your a naught first. So if you find your a naught, and we know that a naught now and this is the general solution for the question. In our previous video, we stated the expression for Fourier transform and then the expression for inverse Fourier transform. We know that a Fourier transform now is what? F of x. All right, so now we have the Fourier transform of a function now, which is this f of x now is equal to this. So if you have any question, you can. So whenever you see an equation like this written as ut equal to beta uxx, all right, this is a short form of its equation, and then you have partial u partial t x comma t equal to beta partial square u partial s square s comma t. Now we are given the length of the wire. Say you have a wire like this now from 0 to L. So this is the length of the wire now. So at this point now, at x equal to 0, which is what we are saying, at x equal to 0, this they are like boundary conditions, because we are given the temperature or the value of the u here and then the value of the u here. So because there is really the temperature is constant here and here, they are both kept at constant temperature, so you have the same value for u, and then for um u equal to 0, sorry, at x equal to 0 and at x equal to L. Yeah, now we are given, we call these are boundary conditions. This is the general solution for its equation. So it's very, very important for us to note this. So whenever we are given a particular question, we're going to solve examples as regarding this equation subsequently. So whenever we see its equation problem, you are expected to know this formula offhand or know how to prove it, because you might ask to prove it. So it's very, very important to know how to prove this. Everyone, welcome to Study Smart platform, and welcome to MTS316 tutorial, where we have been dealing with its equation and how you can solve them. In the previous video, we proved its equation step by step. So here we are going to be doing some examples on its equation, and it's very, very important for you to note these examples because they are exam questions. So please note them as I take you through the solution of these examples. Thank you. So example 1, we are asked to find the solution of the its equation, partial u partial t equal to 7 partial square u partial x squared. We are given the boundary conditions. The boundary conditions always come first. And this is the solution for the its equation. So here we are treating another form of equation that we have to be um, wave equation solution, like solution of wave equation using method of variable separable, or method of separation of variables. So now we have, you see the some likeness now, or some similarity between its equation and wave equation. Its equation is like it has first derivative and then second derivative, but for wave equation now, the two derivatives, they are second derivatives, they are second order derivatives. Then this constant now, it's like the it's a function of what we call wave parameters. So wave equation, whenever you hear wave equation, is came into being because of vibration of springs, and then, or any spring, any spring you can think about, of x. All right, so now we start by using separation of variable to solve this. Now you replace, I said you assume a solution of what? U. So this is now the general solution to the wave equation. Applying initial conditions, now you have f of x, then you have g of x. So it's very, very important for you to note that g of x, now we are comparing your values, your sign does not stand alone. So it is multiplied by what? N pi alpha over L. So please just note that. In the previous video, we proved wave equation till the last end. Now here we have an example here where we are asked to find the solution to a vibrating spring. So whenever you see finding solution to a heat flow problem, that's conduction, you use heat equation. That means they're referring to heat equation. Whenever you see a vibrating spring, because waves are generated from vibration, so you see them using a vibrating springs, using vibrating spring rather. Now we have partial square. All right. So this is now the solution to the heat, or to the wave equation rather.